Hello, AP Physics 1 class. We are going to go over some problems in Chapter 10 on simple harmonic motion that we have not had time to go over in class. This is number 15 I'm looking at first. It's about the springs attached to the wheels of a car. And so here's what it says. The mass supported by each spring is 320 kilograms. A person pushes down on the middle of the front axle or the front end of the car and notices it vibrates 5 cycles in 3 seconds. 5 cycles or 5 oscillations in 3 seconds. That should make you think of the frequency, because frequency is oscillations per second. If I divide that out, I get 1.67 hertz. That's the frequency. The question is, what's the spring constant, little k? And the easiest way to work that problem is to remember this version of the equation. Omega, or angular frequency, is spring constant, is the square root of the spring constant divided by the mass. And then if you remember, omega is also 2 pi f. That's equal to the square root of k over m. Now it's just plugging in the numbers, you know. Use 1.67 for f. Use 320 for the mass. And you can't see that. There it is. There you go. Solve for k. If you do that, you'll get 35,000. The spring constant rounds off to 35,000 newtons per meter. There you go. All right. That is number 15. Number 17 is next. It tells me, hold on, let me erase this. It tells me that there's a block of mass 0.75 kilograms. That's the mass. And it tells me the spring constant is 82 newtons per meter. It's given a displacement of positive 1 or 0.12 meters. X is 0.12 meters on the positive side. And then release from rest. What is the force or magnitude and direction that the spring exerts on the block just before the block is released? Well, that's going to be F is equal to negative kx. And the question is the force, so that would be 0.12 times the K82. There you go. K times X. And that will come out to be 9.84 newtons. Technically, it's negative 9.82 newtons. If you left off the negative, I don't think that would matter. Here, it's just how many newtons of force is the spring applying. It is pulling it back in the negative direction. So that's the reason for the negative. That was part A. Part B asks the question, find the angular frequency of the resulting oscillation. And the easiest way, probably, this is A, the easiest way to find omega, I think here again, like number 15, is to remember this equation. All of these can be worked in different ways, but since that's the question, and you know both k and m, that's now an easy way to do it. Just plug in the k, which is 82, and the m, which is 0.75, and solve it for omega. So it's equal to the square root of k, 82, divided by m, 0.75. And that comes out to be 10.5 radians per second. That's the answer to part B. Part C asks the question, what is the maximum speed of the block? For maximum speed, the easiest way, now you could use energy methods here, where K max is equal to U max. But I think easier would be if you remember that we learned this equation where the maximum speed is equal to A times omega. And we've just found the omega to be 10.5. And the amplitude was listed when it said that the distance it pulled it back was 0.12. And again, the omega we just found is 10.5. So I believe that will give us the correct answer, which is 1.26 meters per second. That's the fastest the mass will ever be moving. That's part C. And then D, determine the magnitude of the maximum acceleration of the block. Okay, that's part D. And for maximum acceleration, you realize that's when it is at the maximum distance from the equilibrium position. And there are always more than one way to work it, but here's an easy way. You have learned this equation, A max, this is acceleration, is equal to amplitude times omega squared. And if you do that, you will get something like 13.1 or 13.2 meters per second squared. That's an acceleration. Now I'll just point out you could have also simply set up F equals ma, which is equal to negative kx. Because you've got x and k and m, solve that for a, you would get the same thing. That would be an easy way to do it too. All right, that is number 17. So let's go to number 19. A person bounces up and down on a trampoline while always staying in contact with it. That's simple harmonic motion. And it tells you that it takes 1.9 seconds to complete one cycle. One cycle in 1.9 seconds. That's the period. I'll write that up here. This is number 19. And the period is 1.9 seconds. The height of each bounce above equilibrium is 45 centimeters. So that's actually the amplitude, 45 centimeters. And then it also tells me, well, that's it. The question is, A, what is the amplitude? Well, doggone it, we just figured that out. That's 45 centimeters. And hold on. That's just the definition of maximum height is amplitude. So that was A, 45 centimeters. B, the question is, where are you? Here it is. B, the question is, what is the angular frequency of the motion? And I think we could invert the period to get F, and we know the period is 1.9, and then angular frequency would be 2 times pi times F. That would be an easy way to do that. So the frequency would be 1 divided by 1.9, and then if you take that and that turns out to be 0.526 hertz. That's the actual frequency, but if you then multiply that times 2 pi, you'll get omega. And omega comes out to be 3.31 radians per second. 3.31 radians per second. That's the unit for angular velocity, or in this case, angular frequency. You can't see that, can you? There's the answer. It's just 2 pi f. Okay, that was part B, I think, in number 19. Part C, what is the maximum speed obtained by the person? And once again, I think I'll do it up here where there's some room. I'll just erase this. The maximum speed, again, could be done with energy methods where K is equal to U, but it's probably easier if you want maximum speed to remember that you can find that by amplitude times omega. And that will give me 0.45 is the amplitude in meters, and omega is 3.31. We just found that. If you multiply that, you'll get the maximum speed in meters per second. That's why we had to change this to meters, so this would come out in meters per second, and that's 1.49. Okay, there's the answer to part D. That was number 19. Okay, that brings us to number 25. The next one we're going to do. 25 had these diagrams where there's a spring attached to the wall, and then there's a mass attached to the other end of the spring. Equilibrium was back here in the first diagram, and the block starts out 1 meter away here. That's 1 meter. And the block is stretched all the way over to here, where it is at 3 meters. Right? Is that really true? Yes, its position is 3 meters from equilibrium. So that's +1. This is +3. So it has moved 2 meters. Now the question is, in number 25, I think, the work done. Is that right? Determine the total work done by the restoring force of the spring. So the question is, how much work is done by the spring? Now, when the spring's pulling back to the left, but the block moves from here to here. Therefore, you already know the spring is doing negative work on the block. The spring's pulling to the left, but the block moves to the right. It's like me pulling on the cow, but the cow moves me. I'm doing negative work on the cow. See? Okay. Negative work is being done. Well, how much? We can't use force times displacement because we don't know anything about the force of the spring. But we can use potential energy here and potential energy here. The difference in potential energies must be the work done by the spring, because there's no other friction or any work being done by anything else. And the question is about the spring anyway. Okay, so this is 1/2 kx squared. This is 1/2 kx squared. And so calculate them both and subtract. I think I have probably calculated them both. This one looks like it is -23 joules at this point. And this one is at -207 joules. Okay, hold on. Now, even if you didn't make them negative, if you made them both positive, you're going to get the right answer if you keep in mind that the work done has to be the change in potential energy. The work done is the change in potential energy. And that change is, it ended up at 207 and it started with 23. So that difference is 184 joules. But the work is negative. If you want to get negative, you've got to plug in some negative numbers like we had before. But if you just did that, and when you subtract, you get this, you would know to make it negative because the block is moving to the right, but the spring is pulling to the left. So you know it's doing negative work. And the amount of work it does is equal to its change in potential energy. Okay. So that's A. B has the block moving from the -3 position to the +1 position. So for B, I would look at it like this. It starts way back here at -3. -3. It goes to 0, and when it goes from here to here, the spring is doing negative work, because the spring is doing positive work because it's pushing to the right and the block's moving to the right. So there the work is positive. Once it passes the equilibrium position and goes over here to 1 meter, it's doing negative work because the spring is pulling back to the left, but the block's still moving to the right. So here work is negative. So get the change in U, but here it's positive, then get this change in U, but here it's negative, and add them together. All right, when I did that, I got 207 when it goes from here to here, but we now know that's a positive 207. And again, that's 1/2 kx squared, where x was 3. Change from this to this. And that's it's positive because F of the spring is the same direction as x. Then over here, the work for 1 is 23, but we know that's negative 23 joules. Yes, it was 23. Now you're going to combine these numbers, and this answer comes out to be a positive 184 joules. It's still, you've got to combine the work done to get it here with the work done to get it there. This one's positive, that one's negative. The net work done for the whole trip is positive 184 joules. And then when you go to C, it goes from -3 all the way up to +3. So +3 is way up here. It's going to do, it goes from -3 to 0 doing positive 207 joules. Then it goes from 0 to 3 doing negative 207 joules. Now 1/2 kx squared is 207. Here you know it's positive because the spring's pushing the same direction it's moving. Positive work. But from here to there, you know it's negative because the spring is pulling backwards, but the block's still moving forward. It's doing negative work, slowing it down. And if you add these two numbers, the answer to part C then, the spring is doing 0 work. There's your work equals 0. All right, that's part C on number 25. All right, I think we're recording again. I just took a break for flex time. I'm recording this Tuesday afternoon. Now, we're on number 29, which I've drawn on the board here. 29 says there's a vertical spring with the mass 2 kilograms hanging from it. The spring constant is 50 newtons per meter. And then the mass is pulled down 0.2 of a meter and released. So it would be kind of like this. It's hanging at rest there. It's hanging at rest, it's not moving. And then you pull it down 0.2 of a meter and let go of it, so it starts to do that. Just to give you the picture of what's going on. Okay. And the question, we know the spring constant, we know the mass. The question is, for number 29, the question is to fill out this chart. At the different heights, what kind of energy does it have? There's the bell to start 7th period. Okay, just so you know where I am. All right, so we need to fill out this chart. And what we know is that when it's down here, that's considered H equals 0. The block's never going to get any lower than that. So when it says 0 up here, it's talking about this position. Now that position is not moving at all. It's in the process of starting to speed up, going up, but right now its velocity is 0, so KE is 0 at that place. UG is MGH. H is 0, so that's 0 as well. That's the potential energy due to gravity. And then US is not 0 though. US is 1/2 kx squared, where the K we know is 50, and the X we know is the distance it has been pulled down from its equilibrium spot. That's what x is. It's the amount the spring has stretched from equilibrium, and that's 0.2. And that's squared in the equation. And if you calculate that, you will get something like 8. I don't know. I've got it written down somewhere. 8.76. So that's this number, 8.76 joules. Now, the total energy, simply add up all of the energy. So that's the only kind of energy it had at that position. So the total is 8.76 joules. All right. Then you go to point 2 when the block is right here. Now, when the block's right here, it has some kinetic energy. We don't know what it is though. Kinetic energy, of course, is 1/2 mv squared, and you could calculate it if you knew v, because we know the mass, but we don't know v. So I don't know what to put there. I'm going to skip it. Let's go to this. It does have U due to gravity. That's mgh, and h is not 0 now. It's 0.2 of a meter above h equals 0. All right, so for this equation, it's the mass, which was 2, times g, which is 9.8, times the height, which was 0.2. Yes, and if I calculate that, I get 3.92. Well, that's the UG, 3.92 joules of potential energy due to gravity. Now, what about US? It has that as well. That's this number of potential energy due to the spring, and that will be 1/2 K is 50, X. Now, the X, when it's at position 0.2, remember, X is the amount that the spring has been compressed and or stretched, and that is something. It's not 0. It is 29. It is, I don't know what it is, but we know the mass, so we have to figure out what that is. We know the mass, which is mg. When it's right here, the spring's equilibrium position is up here. So when it's here, it has been, let me redraw it. When it's just hanging at rest, its force is mg, and the force of the spring is equal to that. So F equals negative kx, and F is mg, and k is 50, so we can get x that way. Let me see if I have found out what that is. Number 29, F equals negative kx. That would be 0.592, nope. That would be 0.392, maybe, let me look. Hold on while I look. Okay, I believe if I calculate this and solve this for x, can you see where I'm writing? Here we are. F equals negative kx, the F is the mg, the k is 50. If I solve that for x, I'll get 0.392 meters. That's just how far the spring is stretched when it's hanging at rest. It's not oscillating. But that's what's happening here, which reminds me that number up there was wrong. We'll come back to that in a minute. All right, so F equals this. So I now know the x to plug in here is 0.392. So that's the U due to the spring. It's 1/2 times 50 times 0.392. That's when it's right here. And that comes out to be 3.84 joules. That's the number that goes here, 3.84 joules. Now, if you add this plus this, you will get Oops, nope, you can't add this and this. Well, you can, but you already know the total energy has to be 8.76. There you go. Because the total energy has to be the same every time. We know it's going to be that here as well. Total energy never changes due to conservation of energy. From that, we can now go back and get the one that we skipped in the beginning. We said, I don't know what the kinetic energy is. I'm sorry. I don't know what the kinetic energy is, we said, but we found these two, and we know the total has to be this, so I can subtract these from 8.76 to get what the kinetic energy had to be. That's the only way to get kinetic energy here, because we don't know the velocity. So if I subtract these from that, it comes out to be exactly 1. So 1 joule of kinetic energy it had. Okay, that's correct here. But I realize now I made a mistake up here in this number when I calculated the U due to the spring at position H equals 0. That was here. This when I did it for up here, I needed to make the x be the 0.392. 0.392 was how far it moved to get here, and then here it moved another 0.2. So the total x there was 0.592 squared. And that's what should give you the 8.76. There you go. Now we fixed that. Okay, let's do the last one. When is it 0.4, which is all the way up to here, somewhere at 0.4. When it's 4/10 above, now let me kind of draw it right, all the way up to where it was hanging at rest was 0.592. So 0.4, it's still not there yet, it's here somewhere. So it's still moving. I know that because it's not going to stop till it goes all the way up 0.592. It's still moving at 0.4. Okay, so it has a kinetic energy, I just don't know what it is. Let's get the rest of them. Ug is mgh, and it is now mass of 2, g is 9.8, but now the h is 4/10 of a meter from the bottom, so 0.4. If you calculate that, you will get 7.84. 7.84. And then you go over to here and calculate the U due to the spring. That's 1/2 kx squared, and that's going to be 1/2 times k, we know, is 50. The x, remember, is the distance it is stretched from the top. And that's going to be the total distance, 0.592, minus the 0.4. 0.592 is when it's all the way up here unstretched, and 0.4 is where it is now. So the spring is still stretched that little amount, which is 0.1, looks like it's 0.192. So I'm going to put 0.192 here for the, okay, that's what I was talking about a moment ago. The total height minus the 0.4 is how much the spring is stretched. And so squared, that should calculate to be the US. And the U due to S, the spring, is 0.922. Now, I could add this together and subtract it from this to get K. But when I add this together, I get 8.76. And so K must be 0. All right. That's number 29. All right, we're going to do one more. I know it's already been almost a half an hour. But for number 33, that's what this is. There's a horizontal spring, a mass that's 0.01 kilograms attached, frictionless. The spring constant is 124 newtons per meter. And the question is, if you give it a push, this is number 33, The block is shoved parallel to the spring axis and is given an initial speed of 8 meters per second. Velocity here is 8 meters per second. Okay, then the question is, what is the amplitude of the simple harmonic motion? The question is amplitude. Okay, energy methods, I think, when you first push it, it has kinetic energy, and when it reaches its amplitude over here somewhere, that's the amplitude, it has potential energy due to the spring. They have to equal each other. And so I can just simply set up K is equal to U. The K is 1/2 mv squared. The U is 1/2 K amplitude squared. I'm going to put x squared because that's the way we write it, but that x is the amplitude. That's what we're looking for. All right, so this is pretty simple now. The mass is 0.01. The velocity is 8 squared. And then over here I have 1/2. The K is 124. And solve that for x. And that x, I believe, comes out to be 0.0718 meters, if indeed, there you go, if indeed you are rounding to 3 significant digits. All right, that's number 33. Hope you understand these. Go over this and ask me questions if you still have them. When I see you. That's it. Have a good day. Bye-bye.